My name is Kirby Lockard, and you're watching one of the Design Drawing Videotapes. This is a series of 10 tapes designed to help students of architecture, landscape architecture, and interior design learn to draw freehand perspective sketches. This is the very first tape in the series and introduces 3 tapes that have to do with perspective construction. We'll be talking about the geometry that you need to master to learn perspectives, how you choose an eye level, and how you use that geometry to lay out exterior and interior perspectives that use what we'll be calling the direct perspective method, so that you're not dependent on plan projection but can draw perspectives straight up right away as soon as you have any idea about the shape and configuration of the space. The first thing, well, I should say that the tapes, like all the other tapes in the series, you're going to need to draw along with me to get the benefit from the videotapes. They're designed for you to draw with me. They're at a pace, recorded at a pace where you can keep up with my drawing. And for that, you're going to need 2 markers, a medium marker and a rather fat marker. You're going to need 3 Prismacolor pencils, preferably red, blue, and green, which are the ones I'll be using. You may want also to have 3 colored markers in red, blue, and green. And you'll need some tracing paper, just ordinary, inexpensive buff tracing paper, which you may want to tear into sheets before we begin, so that you don't have the time-consuming problem of ripping the sheets off of the roll. You'll also need the set of perspective exercises that come along with these videotapes. Now, if you have a lot of experience drafting, if you've had a lot of instruction in drafting, or if you've worked in a position where you were a draftsperson, you may be addicted to the T-square and triangle. And one of the first things you need to do is sort of give up that kind of straight edge dependency. Like any kind of dependency, it is limiting in the freedom you have, and for a designer to have to depend on being at a drafting board with a T-square and triangle in order to think of any design ideas is a real drag. So the first thing we need to do is practice drawing long, straight, freehand lines. So pick up your fine tip marker with me, and let's just draw some of those. Now, some people can draw long, freehand, straight lines by moving their entire hand over the paper, as I'm doing here. Other people find it a lot better to move their fingers, leaving the foundation, leaving the heel of their hand on the paper, so that it doesn't move, and then simply draw the longest straight line you can with a finger motion, and then reposition your hand and patch the line so that you can extend it. Either one of those ways is fine. I use both of them. The way to improve your ability to draw freehand lines is to draw 2 dots and try to connect them with a single line. Now, the first few times you do that, it's a little difficult, particularly if the lines are a long distance apart. See, I missed that one. The other thing you should be conscious of is how you hold the pen. With the public schools these days almost ceasing instruction in penmanship, we find all sorts of strange ways that people hold pens. It's a miracle that they can write at all. The standard way is to lay the pen on your middle finger like that and hold it with your thumb, and then put the index finger down on top of the pen or pencil like this. Now, you may have some slight variation that you're more comfortable with, but if you're not particularly happy with the grip you use, try this one. The other thing you need to be aware of is that your hand physiologically works better in one direction than it does in another, and you need to discover this. I, for instance, can draw my best lines top to bottom and left to right. And the way the hand works, I probably can draw my very best lines from lower left to upper right. But you need to discover those postures which will allow you to draw your very best lines. Some of the best freehand delineators that I know of never tape the paper down. They deliberately leave it loose so that if they have to hatch a series of parallel straight lines, they can turn the paper so that they can put their hand in the very best posture to do that. If you tape it down, your only alternative is to change your body posture, get up and walk around the table, or to avoid the awkwardness of putting your hand in a very bad position. Okay, now if you have become comfortable with drawing freehand lines, a little comfortable, we're ready to begin. Remember that you need to draw with me more than you need to listen. The first few times through the tapes, it's much more important that you keep up with my drawing and then to try to understand all the verbal description I'm giving you. You can get that later from books or from another session with the tapes, but the most valuable thing in these videotapes is for you to actually do the repetitive drawing that's being asked for. So don't just watch them like you were watching television. Actually pick up your pencil and keep up with me as best you can. We're going to call this eye level, and what it represents is the level of our eyes. It's sometimes called the horizon in other perspective methods, but I think it's better if you think of it as your eye level. And let's draw a person standing out in front of us with that eye level running right through his or her head so that it reminds us that that person is on the same eye level we are. We share that eye level. Freehand line number 2, draw a vertical freehand line down the left side of your paper and another one down the right side. Okay, now draw a vertical line right about here and begin it about as far below the eye level line as this figure's feet are below, and then match the distance above like that. So what we have is a vertical line, half of which is below the eye level line and the other half above eye level line. Now for some more straight freehand lines. We need to go from this point to the top of that line and from the top of that line to this other point. And then we need to do the same thing with the bottom. And then you need to try to visualize these two triangles as vertical planes, vertical walls, because we're trying to make this two-dimensional piece of paper into three-dimensional space. And it begins by your being able to perceive these two triangles as vertical standing walls, which are intersecting at this corner. The next thing to do is guess what looks to you like a square standing in this plane, or mark off what looks to you to be a square on that wall. Then come over on this wall and mark off a similar square. And when you've done that, and if it's a little wrong, just draw another line. When you've done that, go from the top of that line to this point, from the bottom of that line to this point, then from the top of this line to this point, and the bottom of this line to that point. And you should be able then to draw the back corner of this cube, because that's what we've been trying to do, is draw a cube. Take a minute and notice how big the cube is. It's about 5 feet from human eye level to human foot level, so that this is always pretty close to 5 feet. Now, we have a cube that is twice that high, so we have a cube that is 10 feet on a side. Take just a moment and look at the configuration of the cube. Notice that it's made up out of 3 parallel sets of planes, 3 pairs of parallel planes. It has a top, and if you have a red pencil, let's color the top red. The ceiling, or the roof of the cube, red. So it has a top and a bottom. These are 2 planes that are parallel to one another, and they're both horizontal planes. It also has a front and a back. The front we'll color blue. If you have a blue pencil, color it blue, please. And the back is also a vertical plane parallel to the front. Now the 2 remaining faces are also vertical planes parallel to one another, and they're represented in our language as, say, the left side and the right side. Now take a minute and make sure you can visualize that cube. Take a minute and look at the top and the bottom as a pair of planes, the front and the back as a pair of planes, and the left side and the right side as a pair of planes, because you need to be able to make that visualization and clearly understand it before we can go on with the perspective principles. We're going to use this little cube to demonstrate the 3 principles of perspective. They apply to all perspective methods, and they are the most basic understanding of perspective. Perspective's been around a long time. It was discovered in the Renaissance, And ever since then, people have been trying to improve on ways of drawing three-dimensional space. But most of the principles were understood pretty well in the 15th century. Let's take a moment now and understand the very first principle of perspective. And it is that sets of parallel planes vanish into lines at visual infinity. Let me overlay this, and would you please overlay this with another piece of tracing paper. And now we're going to just draw particular pieces of this cube. Let's draw the framework, the two vertical lines and the horizontal eye level line. And then draw just the top ceiling plane of the cube and the bottom floor plane of the cube. And I think you can see how easy it is to trace something once you have an underlay under it. The lines immediately are drawn more confidently and with a lot more accuracy. Now let's color those two planes in, and let's understand the first principle of perspective. And this is it. If you push those two planes to visual infinity, they will disappear into a single line, and the line they disappear into is the eye level line. If you grew up in Kansas, or you've ever been to the seashore, you've seen this principle. You've seen the surface of the ocean disappear at the horizon into this line, your eye level line. You may have seen the Earth's surface disappear into a similar line. So we're familiar with the fact that horizontal planes, if you push them as far as you can, like throwing a frisbee horizontally, or slipping a letter into a mail slot, they will disappear at visual infinity into that horizontal line. The vertical examples of this principle are a little more difficult to understand. Let's put another piece of paper down because I want you to separate the planes. And this time let's draw the two side planes. I should have the black. Let's draw this plane and this plane, the left side and right side of the little cube. And let's color those two planes green. Although we've never seen a vertical surface that was as long as the Earth's surface or the sea's surface, the same optical principle applies. If you push those two vertical planes until they disappeared, until they reached visual infinity, they would disappear into this vertical line, just like the red planes disappeared into the horizon. So you need to color this line green, and you need to remember the relationship between that green line and those green planes. We have only the third set of planes remaining, and let's draw those. You should still be able to see down through the stack of tracing paper to see the back plane and the front plane. And if you have a blue colored pencil, let's color those two blue. And ask yourself, where do those guys vanish? Where would they disappear if you push them to visual infinity? And you probably already guessed, they disappear into the remaining vertical line. If you push those two planes as far as you could until they disappeared from your sight, they would disappear into this vertical line. So we need to color it blue, and we need to remember the relationship between vertical planes oriented like that and this blue line. Now we're going to call the three lines vanishing lines, because those are the lines into which sets of parallel planes will vanish at visual infinity. So we have an eye level vanishing line, and we have two vertical vanishing lines. And we're ready for the second principle of perspective. So let's reach for another piece of tracing paper, lay it down over the stack we already have going, and move the whole stack down just slightly, because we're going to need to reach the top of the page in the drawings that we're going to be working on now. Okay, we're now going to investigate the second principle of perspective, which is that sets of parallel lines converge to single points on the vanishing line for the planes in which they lie. Now that's very awkward verbally. And one of the problems in learning drawing is that if we just pay attention to the verbal explanations, it bores our socks off. You have to draw to understand this. As a matter of fact, your understanding will first be one of eye-hand coordination and the ability to actually draw the stuff before you can explain it. So let's draw those two squares that we were drawing, the blue ones. And understand that these four lines, which I'm going to draw right now, I'm going to heavy up, those four lines make a set of parallel lines. In space, they're all four parallel to one another. And the second principle of perspective is that such a set of lines will all converge to a single point on the plane, on the vanishing line for the plane in which they lie. Now they lie in the blue plane. They're the edges of the blue planes. So they're lying in the blue planes, and they're all converging to a single point on the vanishing line for blue planes. Let's see if that same principle holds for the next layer down. If you'll peel off two layers, we'll go back down to the green planes. And if you'll take, well, we can just do this right on the same piece of paper. If you'll heavy up that line, that line, that line, and that line, I think you can see that they are a parallel set of lines. They're all horizontal lines, and they all converge to a single vanishing point on the green vanishing line, because that vanishing line is where the green planes converge to. That's the line they disappear into at visual infinity. And let's go on down, taking off another layer to the red planes, and understand that if we heavy up these four lines, we'll find that they converge to one of those same vanishing points. And you say, wait a minute, those are the same four lines that we were just doing with the green planes. That's right. These two lines are, as a matter of fact, or these four lines are the intersections of the red planes and the green planes. But for the moment, let's see that, yes, they do go to that same vanishing point. And when we put in the green planes, we'll see that these lines that we've been drawing, this last set of four lines, are common to both the red and green planes. And that illustrates the third principle of perspective, which is that these things that we normally call vanishing points are much better understood as being the intersections of two vanishing lines. Let's see if it works on the other side. Let's see if we take these four lines and extend them until they meet over here. And yes, we can see that these four lines are actually the intersection of the red planes and the blue planes. Now let's understand a much more complicated set of parallel lines. And to do that, let's overlay this piece of paper with a new sheet of tracing paper. And we're going to draw some diagonals. But first of all, and I hope by now you're getting more comfortable with drawing freehand lines, the mileage, just the practice of moving your hand and controlling it with your eye, just that perceptual practice, that hand-eye coordination, is extremely beneficial to your learning to draw freehand. And if you can trick yourself or con yourself or shame yourself, somehow get yourself to draw and have your mind turned on at the same time, your drawing skill will just increase automatically. Okay, now we're going to take a diagonal, and we're going to move this down to about there, I guess. We're going to take a diagonal in this plane. Remember that that's a green plane, and that that plane vanishes into this vanishing line. So this line, lying in a green plane, ought to vanish to a single point on the vanishing line for the green planes. Well, we could check that out to see if that's really true, because this other green square has a diagonal also, and it would be parallel in space to that first diagonal. So if we drew this diagonal in the green plane and extended it, it really ought to come from the same point on the vanishing line. And thankfully it does. It comes from that same point. So this is one of those vanishing points to which a set of parallel lines vanish, but not being the edge lines, these are actually diagonal lines. Let's try it with the other planes. You'll take another piece of paper, draw in the two blue planes, color them blue, and color the vanishing line to which blue planes vanish, blue, and let's see if it works with diagonals in the blue planes. If we draw this diagonal, and we keep it going, we will reach, just a little off the paper, we will reach an intersection of the vanishing line and the extension of that diagonal. And if our principle works right, we should be able to draw this diagonal in this space and extend it, and it should converge to the same line. And I think it does. I think you can see that this pair of diagonals, parallel to one another, converge to a single point on the blue vanishing line. We have one remaining plane to try it in, and that's the red one. And let's peel down a couple of layers until we get to this original cube, and just draw the red planes. And the red vanishing line. And if everything we've been saying is true, they ought to check on this third set of planes. So if we draw the diagonal in the floor and extend it until it crosses the vanishing line for horizontal planes, which is this red eye level line, then we should be able to come back from that vanishing point and draw the diagonal of the ceiling plane. And sure enough, we can. So remember that the second principle of perspectives is the one that is normally talked about most, and that's that sets of parallel lines vanish to single points. But don't forget the other two principles. The first one is that sets of parallel planes vanish into lines, and the third one is that what we normally call vanishing points are much better understood as the intersection of two vanishing lines. We're now ready to talk about the frameworks on which perspectives are drawn, and I need to keep you drawing. So let's begin again with a bare piece of paper and draw a vertical line down the left-hand edge, a horizontal line across the middle, and a vertical line down the right-hand edge. This is what we've been drawing. This is what we've been using to draw the perspectives we've drawn so far. Notice that it's made up out of 3 vanishing lines, 1 horizontal one and 2 vertical ones, and 2 vanishing points. Now, real quickly this time, and let's put it over here. Let's put that vertical line over on the left-hand side. It's the same distance below the eye level line as it is above. Let's draw lines to its top and bottom from each of the vanishing points. Then we're going to guess a square standing in this plane and guess a square standing in that plane. And then we're going to draw lines from the top and bottom of that line to this point, to this vanishing point. And we're going to draw lines from the top and bottom of that line to this vanishing point. The reason I asked you to draw this on the left was so we get over the hang-up of left and right. It doesn't make much sense in perspective drawing to call one vanishing point the left vanishing point and the other one the right. It makes about as much sense as it does in football nowadays. It's much better to talk about tight ends and split ends, or strong forwards and weak forwards, fast forwards or small forwards. Much more descriptive than left and right. For instance, we're going to call this vanishing point the near vanishing point, and this vanishing line the near vertical vanishing line, because our perspective is drawn nearer that vanishing point than it is this one. And this one we simply call the far vanishing point and the far vertical vanishing line. Okay, now this is called the three-line two-point perspective framework. Conventionally, it is simply called this is called a two-point perspective. But I think you'll remember the principles much better if you begin to think of this framework as a three-line two-point perspective framework. Now, all perspective frameworks are based on assumptions about the viewer's relationship to the space. That's the only difference between them. They're all arrangements of vanishing lines and vanishing points, and their differences lie in which assumptions they make about the viewer's relationship to the space. For instance, this particular perspective framework assumes that the viewer is holding his or her head level, and that his or her eye level is right there at the eye level line, and the head is held perfectly level, but it makes no assumption about the viewer's body or direction of sight to the object. You're free to draw this object over here as we did last time. You're free to turn and walk around the space. You can view the environment from any angle you choose. And in that sense, it's much more like the human experience of space. Let's take quickly the other two perspective frameworks and understand their differences. The simplest perspective framework is typically called a one-point perspective framework. And please draw with me those two lines. It simply has one vertical vanishing line and one horizontal vanishing line, and one vanishing point smack in the middle of the visual field. Now, if you take a moment and draw a rectangle like this, and then you extend lines from the single vanishing point and continue to extend them through the corners of that rectangle, you begin to get what could become an interior perspective. It now looks like we're inside a room. And in that sense, they're pretty good for interior perspectives. They show you one dimension of the room. They show you at least how wide the room is. And they have the convenience of your being able to draft this set of horizontal lines. Always you can draft the vertical lines, so that the only converging lines you have to deal with are these four that converge to this single vanishing point. But the simplicity and the ease also carries with it what for me is the most objectionable thing about it, which is that it is a coincidental view of space. By that I mean that it assumes that your body is axially aligned with the room. You're standing smack in the middle of the room and you're looking 90 degrees at the end wall. So in that sense it's sort of a firing squad's view of space, or perhaps a bride's, but it is only available to people who are in particular positions in a room. And therefore it's a very static, coincidental view of space. The third perspective framework, instead of being simpler, is more complex. And we can understand it best by drawing a triangle. If you'll draw with me a triangle like this, because this perspective framework is called the three-line, three-point perspective framework. And unlike the first two frameworks, this assumes that the viewer's head is tipped. It's no longer level, but it's tipped either upward or downward, in this case downward. And what really happens is that you take those two vertical vanishing lines that we've been using in the three-line two-point framework, and you bring them together at the bottom and tie them in a knot so that you create a third vanishing point at the bottom of the framework. Now, this is the way we draw perspective on this framework. If you put a dot right there and draw a line to each of the three vanishing points. And then if you choose some width, like there, and connect that point to the bottom vanishing point and to the right-hand vanishing point, and if you'll select a depth, say there, and connect that to that vanishing point, and that to that vanishing point, and then decide on some point like there, and connect it to this vanishing point and that vanishing point. You can see our little cube, but you can see that it appears to be distorted. It appears to us as it would to King Kong looking down on Manhattan. Maybe Broadway and 42nd Street is way down there somewhere, and this is a helipad on top of the building. So while this is a very dramatic way to draw perspectives, it is also a very unusual way to draw perspectives. If we want to look up at a building, we can simply turn the framework over like this, extend it down so it's just a little below eye level, and now we are looking upward at a very tall building. And there's a person standing on the very top of the building, way up there. So you can see that unless it's your first time in New York and you're walking around with your head tilted, that we seldom look at the environment in this way, but it's good to know about that one perspective framework. We're now ready to talk about perspective methods. Unfortunately, sometimes the principles of perspective, and particularly the frameworks of perspective, are called perspective methods. But perspective methods have a completely different kind of distinction. The various perspective methods are different from one another only in the way they measure space. The problem in all perspective is to turn the flat two-dimensional surface of a piece of paper into realistic three-dimensional space. And let's begin to do that because I want you to see how quickly you can do that. Please draw the eye level line and a figure standing right here. I'm sneaking in a little figure drawing on the way so that by the time we get to that subject in the videotapes, you'll have at least a little practice. Now all we need to do is draw a human figure with the eye level line running right through its head to know that it's 5 feet from that eye level line to the figure's feet. And it's quite easy to turn that dimension sideways. All we have to do is just turn it like this, just rotate it, and we can get 5 feet horizontally in the transverse direction. Now let's draw a figure way back there, a little tiny guy, and realize that back there also it's 5 feet from that guy's eyes to his feet. And I can likewise lay that dimension down back there with confidence. And now let's draw a great big figure up here in the foreground and understand that the same thing applies to all three figures. I know that it's 5 feet from that figure's eye level to his feet at that point in the space of the perspective. The difference between perspective methods is how they determine what this distance in depth is. That's the tricky part. Transverse horizontal dimensions are easy. Vertical dimensions are easy. It's just the depth dimension that gives us all the trouble. And it's how we determine the depth dimension that is the distinction between the various perspective methods. Plan projected methods, which are the conventional ways of drawing perspective, all rely on first drawing the floor plan or having it completely determined. And then they use elements like picture planes and station points to definitely discover what the perspective will look like from this particular point. They use vision rays, and it's all a very tedious drafted procedure. They use something called a true line of heights, which you lay out here at the corner of the building, and it allows you to draw perspectives. Problem is, for designers, that you can't possibly draw one of these perspectives by plan projection until you have completely finished the floor plan and the section or elevations, so that it dooms any perspective drawing to being at least a third drawing in the sequence that you can draw. And that's a shame, because it means that perspectives are not actually drawn until very late in the process after all the decisions have been made, and so they're worthless as a design drawing. The method of drawing perspectives that I promote is called the direct perspective method, which means that you can draw perspectives as directly as you draw a plan or an elevation. You only need to know the size, the dimensions, and the general configuration of them to begin to draw them in perspective. This allows a designer to see the three-dimensional reality and quality of the thing he's designing much more quickly than if she has to wait until the plan is completely determined and until she has invested hours of laborious, meticulous projection to discover at the last moment that the thing is really ugly that she spent all this time on. So let's talk about the main measuring mechanism in the direct perspective method. And to do this, we're going to have to draw once more the three-line, two-point perspective framework that we drew earlier. This time, let's draw the horizontal eye-level line down low, because we're going to need to find some diagonal vanishing points. And this time, let's put that vertical line that's 10 feet high over here on the right-hand side and connect it to the two vanishing points like this. Now let's guess a square standing in this face and a square standing in this face. And remember, try to visualize those as two vertical walls intersecting at this corner. Okay, now I've got to make a little aside to show you the principle we're going to be using in two dimensions. So you can draw with me just up here in the corner of this drawing. Draw the double cross that we use to play tic-tac-toe on, what you might call a tic-tac-toe grid. Okay, there's the grid. Now I think most of you would agree that if we had a 45-degree triangle, we could draw that line by just setting the 45-degree triangle down on our T-square and drafting that line. And then if we move the triangle over to this position, we could draw another line like that, which would mark off a square to the right of the first square that was identical in size and shape. It's simply a method of extending an initial spatial unit by using a 45-degree diagonal. You can see, I think, that it works coming down this way. It'll work going up that way. It works in all four directions. And it will work repeatedly, again and again and again. This is really just a simple geometric method of extending an initial spatial unit by using the 45-degree diagonal. We now need to take that same principle and look at it in three dimensions, in perspective. We're going to take this square, the front square, which we've been coloring blue, and please color it blue with me and color this line blue, because this is where that blue square vanishes. We're now going to draw the diagonal of that square and extend it until it intersects with the blue vanishing line. Now, this vanishing point represents a vanishing point for diagonals, and it means that if we assume that this is the central square of a tic-tac-toe grid, and we need to extend the vertical sides of that square upward and downward, even though they go out of view. Perhaps we'll scoot it up later, and extend the top and the bottom forward. They're already extended backward. Now you need to be able to see that as a tic-tac-toe grid in perspective. What we're going to do now is come from this vanishing point. It's just like having a 45-degree triangle. And we're going to come from here to this point. I may miss the first time. Well, I came pretty close. It's going to be about like that. Okay, that's the diagonal, which is marking off the square above this square. To draw the top of it, we have to go to this vanishing point and draw a line like that. Okay, there we have it. That's the square above the initial blue square. Let's get the one behind it. And if we come from this point to this point, where we go through this top line, we simply drop a vertical down, and we now have the square behind the initial blue square. Let's get the one below it. And we just have to continue this line, and I'm going to have to raise the paper just a little bit to get the intersection of that diagonal with this vertical line. And when I do that, I need to go back to this vanishing point to be able to draw the bottom, and there it is. And that is the square below the initial square. Now let's get the one out to the right of it. And for that one, I need to continue this diagonal. And we can see that we're beginning to get distortion. This now no longer looks quite like a square. It looks a little too long or a little too wide. So that coming very far in this direction, we begin to get objectionable distortion. Now, as long as our eyesight holds out and our pencil sharpness, we can just keep doing that. I can mark off the next square back, and the next square back, and the next square back, okay? All coming from this magic vanishing point, which is just like owning a 45-degree triangle. Now, let's take another piece of paper and overlay this, because right now I want to show you an alternative way of doing what we just did. Doesn't mean you get to forget the first way, because it's very important to know how to locate vanishing points like this. But if for some reason you can't reach such a vanishing point, or you just don't want to mess around with, you've got something laying on your drawing board up there and you can't get it out of the way, and you have this initial spatial unit, please just trace this square over like that. Draw both diagonals this time, and we're going to learn how to extend that square without reaching a vanishing point. Now what we need to draw this time is a vertical through the center like that, okay? So there's our initial square. Now we're going to take a line from this point through this point and keep it going until it intersects that line. And then we're going to raise a vertical. That represents, if this is 5 feet, this is 5 feet, that represents another 5-foot increment. And we can just keep doing that. We can make repeated extensions of that initial 10-foot square a half a square at a time. We're just doing it 5 feet at a time, but I think you can see that you could just keep doing that. Now, what actually happens is that these diagonals still really converge, and they still will converge to the same vanishing point. In other words, geometrically, what we have done is absolutely legitimate. You have exactly the same result. It's just that in this case, for whatever reason, you don't have to reach the vanishing point. So the two methods of extending an initial spatial unit are either to find a vanishing point for the diagonal, so you might call this the vanishing point method. The alternative method is called using a diagonal through the bisector. And maybe if I write that down, and if you write it down with me, you'll tend to remember it a little bit longer. Diagonal through the bisector. Now you should know how to do both. You should know how to find a vanishing point and also how to extend spatial units with just the geometry of the bisector. Let's try it in one other plane just so you understand. Can we go back to this one, please? You must have that in your stack someplace. If you'll take another piece of tracing paper and slide it over this one, retrace what was the green plane, or the green square, here, and remember that the green square vanishes into this vanishing line. And to remind ourselves of that, let's color that one green and color the vanishing line green. And I think we ought to put in at least the eye level line, or maybe the other vanishing line also. Okay, now we need to draw the diagonal in the green plane and extend it until it intersects the vanishing line for the green plane. Then we need to extend these two edges the vertical edges of the green plane because we've got to make that tic-tac-toe grid. And we need to extend also the top and bottom of the green plane. Now, we should be able to come from this vanishing point for diagonals to this point, like this. And where we go through the back vertical line, we can draw the top of the next square above the initial green square. There it is. And if we keep that diagonal coming, we will mark off the next square in front of the initial green square. Now we need to go back to the same vanishing point for diagonals and go from it to this lower right corner of that initial green square like this. And when we do that, and just keep coming, when we do that with a single diagonal, we mark off the other two squares. All we need to do is drop a vertical from there, and we need to go from this point to this vanishing point like that. Now I think you can see the same cross-shaped collection of 5 squares. The initial green square, which we started off with, and the 4 squares which are tangent to that initial square, all discovered or marked off by using the vanishing point for diagonals. Let's draw one more 3-line 2-point perspective framework and just make sure we understand how you would put to use these principles we've been talking about. Let's draw the eye level line. Let's draw the 2 vertical vanishing lines. And let's draw that vertical 10-foot line right there this time and connect the top and bottom of it to the respective vanishing points, like this. You should be able to do this pretty quickly now. It helps if you hurry your drawing once in a while. You need to have more than one gear. It's no good if the only thing you have is sort of low gear. You need to have a mid-range and then a real high gear like overdrive when you need it, because a lot of times in designing, you're almost out of time. Okay, I think you'll understand now that in drawing an exterior perspective, we can set it up like that, and as long as this looks like a believable 90-degree angle, we're just fine. We can begin to draw a building on this framework. You guess the first 10-foot square, you draw its diagonals, and then you simply extend that until you get as big a building as you need. We're dividing into 5-foot increments, so that right now we have a building that's 10, 15, 20, 25, 30 feet long, and we can just keep doing that. If we draw a bigger building, we may need a bigger framework, or we may need to start with bigger squares, but the method will replicate the initial spatial units so that we can measure that plane to any size we like. What we need to talk about for just a moment now is how we subdivide space using a diagonal. And for that, we need to draw one more framework. I'm tricking you into drawing as much as I can, and you'll notice that we've drawn by now a whole bunch of those long freehand lines, so you should be getting comfortable with that. We're going to draw one more across here, draw the 2 down the sides, and this time we're going to draw a figure right there, just to remind us that that's the eye level, and don't worry about whether your figure is a decent figure or not. We won't worry about that too much. And over here, let's put a line like this that is 5 feet above and 5 feet below eye level, and connect it to the 2 vanishing points. And then we want to guess what looks like a square in that wall and in this wall, so that we have our familiar 10-foot cube. I may have guessed mine a little bit short, but not too much maybe. Now let's draw the 2 diagonals. Whoops. There, that's better. and this one, and draw a vertical line there. And understand that when we've done that, we have divided that 10-foot square into 4 5-foot squares. There's one, and down here's another. And if we want further measurements within that, we can easily get them. We can draw this diagonal, and we have now subdivided that square into 4, we have to go back to this vanishing point to draw the horizontal, into 4 30-inch squares. And one of those is here. We can now subdivide that even further with another diagonal, and we get 4 15-inch squares. And if we wanted to, we could divide it once more and get 4 7.5-inch squares. So that the diagonal is useful not only for extending space, but for subdividing it. And as a matter of fact, we need no further measurement ability. We can do it all with the diagonal. I'd like to point out the usefulness of this particular set of measurements. First of all, it starts with human eye level, which is not an arbitrary level. It's a level we all share. If you double that, you get 10 feet, and we're all familiar with a math base of 10, so that's a fairly comfortable measurement. If we subdivide the 5 feet, we get a 30-inch square, or a 30-inch cube, and a 30-inch cube is a perfect furniture module. Most furniture is made up out of some multiple of 30-inch cubes. One cube is about the size of a club chair or a bridge table. 2 cubes put together is about the size of a sofa or exactly the size of an executive desk. If we divide it further into 15 inches, we get seat height, at least lounge seat height, and another 7.5 inches, and then we're at stair riser height, the maximum riser that's allowed by the building code. So you see we have a very useful set of dimensions. The thing I'd like to point out about this direct perspective method, which the next 2 tapes will deal with in more detail and help you understand how to draw exterior and interior perspectives. One of its best features is that it doesn't rely on an architectural scale or on a straight edge. Notice that we've drawn space and been able to measure it precisely based entirely on the dimensions of the human figure and on our ability to draw straight, freehand lines.